Fine. Let's start. Number 14. The moon that holds the Earth steady. Look up at the moon tonight and you'll see a rock. A nice one. Good for tides, good for poetry, good for werewolves. What you won't see is the fact that it is quietly holding your planet upright. Earth spins on an axis tilted about 23.4 degrees. That tilt is why we have seasons, why the year has a rhythm, why the whole living system you belong to runs on a predictable calendar. And that tilt barely moves. Over tens of thousands of years, it wobbles by about a single degree. Almost nothing. Here's why. Our moon is absurdly large for a planet our size. It's a quarter of Earth's width, and that mass acts like a gyroscope, gripping our axis and refusing to let it swing. We are, in a very real sense, held in place by our own satellite. Now here's the part that got scientists' attention. In 1993, a French astronomer named Jacques Lascar ran the numbers on an Earth without a moon, and the models went wild. Without the moon's grip, our axis would not gently wobble. It would lurch. Lascar found it could swing chaotically anywhere from 0 degrees, lying nearly on its side, all the way past 85 degrees. Imagine the poles baking under a vertical sun while the tropics freeze. No stable seasons, no reliable climate. Possibly no us. For years, that was the story. The moon is the reason Earth is calm enough for life. A lucky, oversized bodyguard we happen to be born with. But then, the story got more honest, which is usually when it gets more interesting. A later study in 2012 softened the picture. A moonless Earth, it turned out, probably wouldn't go fully insane. It would wobble more, maybe 10 degrees or so, but it wouldn't necessarily cook itself. The moon isn't the only thing keeping us stable. It just helps. And here's the sting. Even with the moon, the calm is temporary. The moon drifts away from us about 3.8 centimeters every year, and Earth's spin is slowly winding down. Lascar's own math says that in roughly 1.5 billion years, our tilt will start to go chaotic anyway. Moon or no moon. So the steadiness you're standing on isn't a permanent gift. It's a lease. And the quiet rock in the sky is just buying us time. Number 13. The rings we arrived just in time to see. Saturn's rings are the most famous object in the solar system that isn't a planet or a star. Every telescope points at them. Every kid draws them. They feel eternal, like they've always been there and always will be. They haven't. And they won't. When the Cassini spacecraft ended its mission in 2017, it did something no probe had ever done. It threaded the gap between Saturn and its rings 22 times, letting the planet's gravity weigh the rings directly. And the rings came back light. Only about 40% of the mass of Saturn's little moon Mimas. That matters, because a lighter ring is a younger ring. Rings get polluted by cosmic dust over time, like snow going gray by a roadside. Saturn's rings are still bright, still almost pure ice, which means they haven't been out there long. The best estimates put their age somewhere between 10 million and a few 100 million years old. Sit with that. The dinosaurs were already long gone by some estimates, or still walking around by others. But either way, on the scale of the solar system, these rings are brand new. Saturn spent most of its 4.5 billion year life with no rings at all. And then, recently, cosmically speaking, it put them on. Now the other half. They're also dying. A scientist named James O'Donoghue measured something called ring rain, water from the rings being pulled down into Saturn's atmosphere. The rate is brutal, enough to drain an Olympic swimming pool's worth of ring material into the planet roughly every half hour. At that pace, the rings have maybe another 100 million years before they're gone. So the rings are young, and the rings are vanishing, which leaves one strange, quiet fact hanging in the air. Saturn has worn rings for a tiny fraction of its existence. And we showed up during that fraction. Not before, when there was nothing to see. Not after, when they'll be gone. Now, right in the narrow window, when the most beautiful structure in the solar system happens to exist and happens to be visible. Some astronomers push back and say the rings might be older than we think, or that 100 million years is still a wide window, not a miracle. Fair enough. But the timing still lands with a little chill. We are, in the most literal sense, here for a limited engagement. Number 12. The ocean that's thinner than it looks. Water covers about 70% of the Earth's surface. From space, we are the blue planet, the wet world, drowning in the stuff. So here's a number that should feel wrong. All the water on Earth, every ocean, every sea, every drop, adds up to about 0.02% of the planet's mass. 0.02 of 1%. If you could gather every ocean into a single ball and set it next to the Earth, that ball would look shockingly small. A little blue marble beside a huge dry rock. The oceans aren't a reservoir. They're a film. A thin, shining coat of varnish on a ball of stone. If you shrank the Earth down to the size of a billiard ball, it would be smoother and, proportionally, drier than the billiard ball in your hand. And that thinness turns out to be exactly what we needed. Here's the tension. You want water. Life needs it. But you don't want too much. A planet with far more water than Earth doesn't become a nicer Earth. It becomes a water world, an ocean with no bottom you'll ever reach, and, crucially, no land. No continents poking up. No exposed rock. An exposed rock, it turns out, is not optional. Researchers Nicholas Cowan and Dorian Abbott modeled this and found that a planet stays a normal world with continents only if its total water budget stays below roughly 0.2% of its mass. Go much past that and the land drowns. Earth sits comfortably under that line. We got enough water to fill oceans and little enough to keep our continents dry. Why does land matter so much? Because of what's coming in the next entry, the machinery that keeps this planet's temperature stable relies on bare rock meeting air and rain. Drown the rock, and you switch off the thermostat. A water world can be soaking wet and still spiral into a climate that never settles. And one more strange detail. There may be more water hidden inside the Earth than in all the visible oceans combined, locked deep in the mantle inside minerals, with names like ringwoodite, water that is not liquid, not ice, just bound into the crystal itself. So the ocean you picture as bottomless is a rounding error on the planet's mass. And it's a rounding error tuned almost perfectly. Enough to fill the seas. Not enough to bury the shore. Number 11. The clockwork nobody wound. Point a decent telescope at Jupiter, and you'll see it flanked by 4 bright dots. Galileo saw them in 1610 and realized they were moons, orbiting something other than Earth, which quietly helped end an entire model of the universe. But 3 of those moons are doing something stranger than just orbiting. They're keeping time. The innermost of the 3 big ones, Io, whips around Jupiter fast. The next one out, Europa, takes exactly twice as long. And the third, Ganymede, takes exactly twice as long again. 4 to 2 to 1. Not roughly, not approximately. Locked. For every 4 laps Io runs, Europa runs 2, and Ganymede runs 1. Like 3 runners on a track who can never break stride. This is called the Laplace resonance, named for the French mathematician Pierre-Simon Laplace, who worked out the dynamics in the 1780s. And it isn't a coincidence that happens to look tidy. It's a lock. The moon's gravity nudges each other at the same points over and over, and those nudges hold the whole arrangement in place. A self-correcting gravitational machine. And it has consequences. Those repeated tugs keep squeezing and stretching Io, flexing its interior until it becomes the most volcanic body in the solar system, a moon covered in erupting sulfur. The same flexing keeps Europa warm enough to hold a liquid ocean under its ice. The clockwork isn't just elegant, it's powering worlds. Now the detail that makes people's brains itch. Because of the resonance, those three moons can never all line up on the same side of Jupiter at once. The math forbids it. Whenever Io and Ganymede swing to the same side, Europa is always, without exception, on the opposite side of the planet. The system has a rule, and it never breaks it. It genuinely looks designed. A three-body metronome that powers volcanoes and hides an ocean and refuses to let its parts collide. If you were building a solar system as a machine, this is what the gears would look like. Except no one built it. Resonances like this form naturally. Moons drift slowly over millions of years, and when their orbits fall into a simple ratio, they can catch and lock, the way a slightly pushed swing settles into rhythm. We even see it around other stars now, in systems like TRAPPIST-1, where 7 planets march in a resonant chain. So it's not a miracle, it's just physics falling into step. But when you watch it run, precise, self-correcting, humming along for eons, it's very hard to shake the feeling that the solar system is keeping time on purpose. Number 10. The thermostat no one installed. Here's a problem that should have killed us long ago. The sun is not a stable, constant light. Over its life, it has slowly brightened. Back when the Earth was young, the sun was about 30% dimmer than it is today. By every simple calculation, the early Earth should have been a frozen ball, and today's Earth, under a brighter sun, should be a runaway oven. Instead, for something like 4 billion years, Earth's surface has stayed in the narrow band where water is liquid. Through a dimming and brightening star, through ice ages and hot spells, the planet keeps sliding back toward livable, as if something is adjusting the dial. Something is, and it's rocks. In 1981, 3 scientists, James Walker, Paul Hayes, and James Casting, laid out the mechanism. It's called the carbonate-silicate cycle, and it works like a thermostat with no thermostat in it. Carbon dioxide in the air traps heat. When the planet warms up, chemical weathering speeds up, rain and warmth eating away at silicate rock faster. That weathering pulls carbon dioxide out of the air and locks it into stone and, eventually, the seafloor. Less carbon dioxide, less trapped heat, and the planet cools back down. And it runs the other way too. When Earth gets cold, weathering slows to a crawl. But volcanoes keep breathing carbon dioxide back into the air. It builds up, traps more heat, and warms the planet again. Warm too much, and the weathering kicks back in, back and forth. A slow, patient, self-correcting loop. The knob on this thermostat is, almost unbelievably, the rate at which mountains dissolve in the rain. Something that sounds completely unrelated to global temperature is the exact lever that has kept Earth's oceans from freezing solid or boiling away since before there were animals to notice. And nobody set it up. There's no design here, no purpose. It's just chemistry that happens to depend on temperature, riding on a planet that happens to have plate tectonics constantly serving up fresh rock. Put those two together, and you get a climate that regulates itself for billions of years. But don't get comfortable. This thermostat is slow. It works over hundreds of thousands of years, not decades. So when we dump carbon dioxide into the air in a couple of centuries, the rocks can't respond in time. The planet's self-correction is real, and it's patient, and it is far too gentle to save us from ourselves on a human schedule. Still, a world that quietly holds its own temperature steady through a changing star for eons. It shouldn't feel that easy. And yet, here we are, standing on it. Number 9. The reason falling feels like floating. Drop a hammer and a feather in a room full of air, and the hammer wins. Do it on the moon, where there's no air, and Apollo 15 actually tried this on camera in 1971, and they hit the ground at the exact same moment. Everything falls at the same rate, regardless of what it's made of or how heavy it is. We treat that as obvious. It is not obvious. It's one of the deepest coincidences in physics, and it bothered Einstein for a decade. Here's the puzzle. Every object has two kinds of mass, and they have no obvious reason to be related. The first is inertial mass, how hard it is to push something, how much it resists being shoved. The second is gravitational mass, how strongly gravity pulls on it. One is about resistance to motion. The other is about response to gravity. Totally different ideas. And yet they are identical. Not close. Identical, as far as anyone can measure. We've now checked this to about 1 part in 1,000 trillion. A French satellite called Microscope spent 2 years dropping 2 different metals, platinum and titanium, in a perfect free fall around the Earth, watching to see if one fell even slightly faster. Neither budged. 15 decimal places of agreement. Because those two masses are always equal, the heaviness cancels out of the falling. Gravity pulls harder on a heavier object, but a heavier object also resists that pull harder in exactly the same proportion. So everything accelerates the same. The hammer and the feather, the platinum and the titanium, all of it. Einstein called the moment he understood this the happiest thought of his life, because he saw what it meant. If everything falls together, then a person falling can't feel gravity at all. Step off a roof, and, for that terrifying second, gravity vanishes from your point of view. You float. Which brings us to the thing everyone gets wrong about astronauts. Astronauts on the space station are not floating, because there's no gravity up there. At that altitude, gravity is still about 90% as strong as it is on the ground. They float because they, and the station, and every atom of both, are in constant free fall together, endlessly falling around the Earth and never hitting it. Weightlessness isn't the absence of gravity. It's the experience of falling perfectly. So the next time you watch an astronaut drift across a screen, remember, they're not escaping gravity. They're falling exactly like a dropped feather, and so is their entire ship. And that only works because 2 completely different quantities agree to be the same number, to 15 decimal places, for no reason anyone can point to. Number 8. The universe picked exactly 3 dimensions. You live in 3 dimensions of space. Left, right, forward, back, up, down. You've never thought about it because there's never been an alternative. It just feels like the number of directions the world has. But there's no obvious law saying it had to be 3. And when physicists ask what would happen with a different number, the answer is quietly alarming. 3 isn't just the number we got. It may be the only number that works. Back in 1917, a physicist named Paul Ehrenfest asked this seriously. What changes if space has more or fewer dimensions? He looked at how forces like gravity behave, and he found something strict. The number of dimensions controls how fast a force fades with distance. In our 3-dimensional space, gravity follows the famous inverse square law, weakening with the square of distance. Double the distance, quarter the pull. That specific fall-off is what lets planets hold stable orbits. Add a dimension. Now gravity fades with the cube of distance instead. And in that world, orbits stop being stable. A planet nudged slightly inward doesn't settle into a new orbit. It spirals straight into its star. Nudged outward, and it drifts off into the dark forever. There's no comfortable middle. 4 dimensions of space, and solar systems can't hold together. Now here's the part that turns a curiosity into something eerie. The exact same math governs the atom. Electrons are bound to a nucleus by a force with the same inverse square shape, and it fails in the same way. In 4 or more dimensions, atoms can't hold their electrons in stable orbits either. They come apart. So think about what that means. The one property of space you never questioned, that it has 3 dimensions, is simultaneously the reason planets can circle stars and the reason electrons can circle nuclei. Both the very large and the very small depend on it. Change that single number, and you don't just lose galaxies. You lose chemistry. You lose matter that holds together at all. The physicist Max Tegmark later pushed this further and added a twist about time. If there were more than one dimension of time, he argued, you couldn't reliably predict anything. Cause and effect would dissolve. So it's not just 3 dimensions of space that seem required. It's 3 of space and exactly 1 of time. The precise stage the universe is set on. Now, the honest caveat. This is what physicists call an anthropic argument. If only 3 dimensions allow stable matter, then, of course, any being asking this question finds itself in a 3-dimensional universe. There's nowhere else it could be. Maybe space is just 3-dimensional as a brute fact. No reason required. But it's a strange feeling, isn't it? To learn that the number of directions you can point in is also the reason you exist to point at all. Number 7. The rounding error your body depends on. Inside every atom of you, there are protons and neutrons packed into nuclei. They look like near twins. Almost the same size. Almost the same mass. Almost. The neutron is very slightly heavier, by about 0.14%. In the units physicists use, the gap is about 1.3 million electron volts out of 939 million. A hair. A whisper. The kind of difference you'd round away without thinking. Do not round it away. That tiny surplus of mass, sitting on the neutron rather than the proton, is one of the reasons you exist. Here's why the direction matters. In physics, heavier things tend to decay into lighter things. Because the neutron is the heavier one, a lone neutron is unstable. Left by itself, it falls apart in about 15 minutes, decaying into a proton. And a proton, being the lighter particle, is stable. It just sits there, essentially forever. A proton is a hydrogen nucleus. Stable protons mean stable hydrogen. Hydrogen means water, and stars that burn slowly for billions of years, and the entire chemistry that makes life possible. All of it rests on the proton being the lighter, stabler one. Now flip the gap. Imagine the proton were the heavier particle instead. Then the proton would be the one that decays. Lone hydrogen nuclei would fall apart. No stable hydrogen. No water. No long-lived stars. A dead, sterile universe. And the difference between that universe and ours is a fraction of a percent of mass pointing the right way. And it gets stranger, because we now know why the neutron won. In 2015, a team led by the physicist Zoltan Fodor computed the mass difference from pure theory for the first time, and found it's a tug-of-war between 2 effects. Neutrons and protons are each built from smaller particles called quarks. The down quark is heavier than the up quark, and that pushes the neutron's mass up. But protons carry electric charge, and that charge carries energy, which pushes the proton's mass up. Here's the punchline. Electromagnetism, on its own, would have made the proton the heavier one. It would have doomed hydrogen. We are saved only because the down quark happens to be about twice as heavy as the up quark, and that effect just barely wins, tipping the balance back the other way by that thin 1.3 million electron volts. So your stability, the fact that your atoms don't quietly dissolve, comes down to a contest between 2 forces that nearly cancel, decided by a margin so small it looks like a mistake. Except it's the mistake that lets you be here to notice it. Number 6. The ration decided in the first second. Go back to the very beginning. Not billions of years ago. The first second. The universe is a searing fog of particles, unimaginably hot, expanding and cooling at a blistering rate. And in that first second, a decision gets made that every star for the rest of time will have to live with. In that early fire, protons and neutrons are constantly flipping back and forth into each other. A proton becomes a neutron becomes a proton, endlessly, kept in balance by the weak nuclear force, the same force behind radioactive decay. As long as it's hot enough and the reactions are fast enough, their numbers stay roughly matched. But the universe is expanding, and expanding means cooling. And as it cools, those flipping reactions slow down. Then, at about 1 second in, at a temperature of 10 billion degrees, they essentially stop. Physicists call it freeze-out. The conversions can no longer keep up with the expansion, and the ratio of neutrons to protons is suddenly locked, frozen in place. At that instant, it's about 1 neutron for every 5 protons. That frozen ratio is everything, because in the minutes that follow, almost every surviving neutron gets swept up and bound into helium, while the leftover protons stay as bare hydrogen nuclei. Do the arithmetic on that 1 to 5 starting point, and it lands you at a universe that is about 75% hydrogen and 25% helium by mass, which is exactly what we measure. Look at the oldest, most pristine gas in the cosmos, and it's about 3/4 hydrogen, 1/4 helium. That number was set in the first second by the weak force before a single star had ever shone. And here's why it's a coincidence worth staring at. That ratio was decided by a race between 2 clocks. The weak forces clock, how fast protons and neutrons flip, and the expansion clock, how fast the universe cools and shuts the flipping off. Tune the weak force a little differently. Change how fast that first clock ticks, and the freeze-out happens at a different moment, with a different ratio. Make it lock in with almost no neutrons, and you get a universe of nearly pure hydrogen, with far less of the raw material for later chemistry. Lock it in the other way, and you tilt the whole balance the other direction. There's even a second thread, hanging on the neutron's own lifetime, those 15 minutes we mentioned. If neutrons decayed much faster, hardly any would survive long enough to make helium at all. So the fuel mixture of the entire universe, the exact ratio that would one day allow water and long-burning stars, was rationed out in the opening second by a race between 2 invisible clocks that just happened to cross the finish line together. Number 5. The catastrophe that turned out to be a myth. This one is famous. You've probably heard a version of it because it's the single most repeated fine-tuning story in all of popular science. And there's a reason I've buried it here in the top 5. Because the story is thrilling, and the story is also mostly wrong, which is somehow more interesting than if it were true. Here's the classic version. There's a force that holds atomic nuclei together, the strong nuclear force. It's what lets protons and neutrons stick, despite protons electrically repelling each other. Now, in our universe, you cannot bind 2 protons together on their own. Try to make a nucleus of just 2 protons, something called a diproton, and it instantly falls apart. The strong force is just barely too weak to hold 2 protons alone. And the famous claim, made by the great physicist Freeman Dyson, is that this is a very, very good thing. Because if the strong force were just a few percent stronger, the diproton would hold. 2 protons could stick together directly. And in the blazing furnace of the early universe, that would open a shortcut, letting protons fuse straight into each other with terrifying ease. The result, so the story goes, is that the young universe would have burned through all its hydrogen almost instantly, fusing it away in minutes. No hydrogen left. No water. No slow-burning stars. A universe that torched its own fuel in the first breath. It's a fantastic story. A knife edge. Nudge one force by a few percent, and everything we love is gone. For decades, it was the crown jewel of the whole fine-tuned universe idea. And then people actually ran the numbers. In 2009, a physicist named R.A.W. Bradford, and separately a team of physicists, McDonald and Mullen, did the hard quantitative work. They built universes with a bound diproton and asked carefully what actually happens. And the catastrophe just didn't. It turns out that even if you let two protons bind, the early universe does not burn away all its hydrogen. Plenty survives. To meaningfully deplete the hydrogen, you'd need to crank the strong force up, not by a few percent, but by something like 50%. And stars in those altered universes still work. They still shine. So the scariest coincidence in the catalog, the one everybody quotes, turns out to be a myth that fell apart the moment it met a spreadsheet. And I love that, because it cuts both ways. It's a warning. A lot of these too perfect stories feel airtight until someone checks. Some are rock solid. This one wasn't. The universe didn't dodge a bullet here. There was never a gun. Number 4. The number physicists find embarrassing. In 2012, at the Large Hadron Collider outside Geneva, thousands of scientists confirmed the existence of the Higgs boson, the particle tied to the field that gives other particles their mass. It was a triumph, decades in the making. They measured its mass at about 125 in the units particle physicists use. And then, almost immediately, that number started keeping people up at night. Because it's in the wrong place. Badly wrong. So wrong that physicists have a slightly embarrassed name for the problem. They call it unnaturalness. Let me try to give you the shape of it without the machinery. The Higgs has a mass we measured. But in quantum physics, a particle's mass isn't just one clean value. It's the starting value plus a storm of corrections, contributions from every other particle and field flickering in and out of existence around it. And for the Higgs, those corrections are enormous. They should, by all rights, drag its mass up to something near the highest energy scale in physics, the Planck scale, which is roughly 1,000,000 billion times larger than what we see. But it isn't up there. It's tiny, sitting far, far below where the math wants to push it. And the only way that happens is if all those gigantic corrections almost perfectly cancel out. A huge positive contribution and a huge negative one lining up to erase each other, leaving a tiny remainder behind. How precise does that cancellation have to be? Roughly 1 part in 10,000 trillion trillion. Picture two colossal numbers, each astronomically large, that happen to agree in their first 30-some digits and only differ at the very end. That leftover sliver is the Higgs mass. That's the hierarchy problem, and it's the sharpest case of apparent fine-tuning in all of known physics. And there's a second, darker layer. At the mass we actually measured, the universe's vacuum, empty space itself, sits right on a knife edge. Calculations suggest our vacuum is metastable, stable enough to have lasted nearly 14 billion years, but poised close to the boundary, where, in principle, it could one day tip into a lower energy state. The mass-giving particle didn't just land improbably low. It landed right on the line between a stable universe and a doomed one. Now, the honest part. After the collider searched and found no sign of the tidy solutions physicists hoped for. Like supersymmetry, some have started to wonder whether naturalness was the wrong expectation all along. Maybe the number just is what it is, and our sense that it ought to be different is the thing that's mistaken. Maybe. But it's telling that the most successful theory in the history of science produced one number so strange that its own authors find it faintly humiliating. Number 3. The single number that seeded everything. Look at the universe today, and it's lumpy. Galaxies here, vast empty voids there, matter clumped into a great cosmic web of filaments and walls. But it didn't start that way. It started almost perfectly smooth, a nearly uniform soup, the same in every direction to an astonishing degree. Almost. And that almost is one of the most important numbers in cosmology. In that early smoothness, there were faint ripples, tiny regions very slightly denser than average, and those specks of extra density are the seeds of everything. Gravity pulls matter toward the denser spots. They grow. They pull in more, and over billions of years, those whispers of unevenness become galaxies, clusters, the whole structured cosmos. Every galaxy you've ever seen grew from one of those original ripples. The British astronomer royal, Martin Rees, gave the size of those ripples a name. He called it Q, and he measured how big they were, the depth of the initial unevenness, as about 1 part in 100,000. The early universe was smooth to 99.999%, and it's that last thousandth of a percent of roughness that built everything. Rees called Q one of just 6 numbers that shape the entire universe, and what's unsettling is how narrow the good range is. Suppose Q had been smaller, fainter ripples. Then gravity would have had almost nothing to grab. The seeds would be too weak to grow, and the universe would stay a thin, cold, formless haze. No galaxies, no stars, no planets, just diffuse gas drifting forever in the dark. Now suppose Q had been bigger. Say 10 times bigger. Still a small number. And here's the surprising part. You'd still get structures, but they'd be monstrous. Matter would clump so violently that vast regions would collapse straight into enormous black holes, and the stars that did form would be packed so densely, so close together, that any planet trying to orbit one would have its path constantly wrecked by neighbors passing too close. No stable orbits, no quiet solar systems, no room for a world to just exist, undisturbed, for the billions of years life seems to need. So Q doesn't just decide whether there's structure. It decides whether there's room, whether a universe is spacious and calm enough to hold a planet in a stable orbit around a stable star. And the value we got, 1 in 100,000, sits right in the narrow band that allows exactly that. One number, set in the first fractions of a second. Faint enough to leave the cosmos peaceful, strong enough to leave it populated. Every galaxy, every star, every world grew from that one dialed-in whisper of roughness. Number 2, the most improbable number ever calculated. Everything we've talked about so far has been a knob, a force, a ratio, a dimension. This one is different. This one is about how the entire universe began, and it produces a number so large it breaks the very idea of a number. Start with something you know in your bones. Order tends to fall apart. A cup shatters. It never unshatters. Heat spreads out. It never gathers back. Physicists call the measure of disorder entropy, and the iron rule is that entropy always increases. That relentless one-way slide from order to disorder is, as far as we can tell, the reason time has a direction at all, the reason there's a difference between the past and the future. But run that logic backwards. If disorder always grows, then the past was always more ordered than the present, and the deep past, the very beginning, must have been staggeringly, almost perfectly ordered. The universe began in an extraordinarily low entropy state, incredibly smooth, incredibly uniform. That original orderliness is the reservoir the entire history of the cosmos has been spending down ever since. It's why anything interesting can happen at all. So the question becomes, how special was that beginning? How finely arranged did the initial state of the universe have to be, out of all the ways it could have started? Roger Penrose, one of the great mathematical physicists, actually calculated it. He used the mathematics of black holes to count the possibilities, and the answer he got is beyond human intuition. The precision of the Big Bang's starting order was about 1 part in 10 to the power of 10 to the power of 123. Let me try to make that land, because you can't feel it stated plainly. A big number like a Google is one followed by 100 zeros. Penrose's number isn't one followed by 123 zeros. It's one followed by 10 to the 123 zeros. The number of zeros you'd have to write is itself a number larger than every particle in the observable universe. Sit inside that for a moment. To write this probability out in full, you would need more zeros than there are atoms in the cosmos to write them on. The number describing how precisely our universe began, physically, cannot be written down anywhere inside that universe. There isn't enough stuff. Penrose himself, reaching for words, framed it in terms of how precise a creator's aim would have to be. Most physicists don't go there. They call the low entropy beginning an unsolved problem, and they reach for inflation, or a multiverse, or the possibility that we're just not counting correctly. But strip away the explanations, and the raw fact remains. The universe began in a state so ordered, so unlikely, that the odds against it are the most extreme number science has ever had reason to write, or rather, the number it cannot write at all. Number 1, we live in the only chapter the universe can be read. Here's how we know the universe had a beginning. 3 great clues. Distant galaxies are all rushing away from us, so the universe is expanding, so it was once compressed. A faint glow of leftover heat fills the whole sky, the cosmic microwave background, the afterglow of the hot early cosmos. And the ratio of light elements, that 3/4 hydrogen, 1/4 helium we talked about, matches exactly what a hot Big Bang should produce. 3 independent lines of evidence, all pointing back to the same fiery origin. It's one of the great triumphs of the human mind. Now here's the thought that should quietly rearrange something in your chest. That evidence is not permanent, and the window to read it is closing. 2 physicists, Lawrence Krauss and Robert Scherer, worked out what the universe will look like to astronomers in the far future. Not the end of the universe, just later. Because the expansion of space is speeding up, driven by dark energy, distant galaxies are accelerating away from us. And eventually, they'll cross a kind of horizon, receding so fast their light can never reach us again. One by one, the galaxies wink out of view. Give it roughly 100 billion years, and every galaxy outside our own local group will be gone, vanished past that horizon. The sky will hold only our own merged galaxy, surrounded by perfect, endless black. And it gets worse. That afterglow, the cosmic microwave background, will be stretched by the expansion until it's too faint and too long to detect at all. Gone. And the leftover hydrogen and helium will have been reprocessed by generations of stars, erasing the original ratio. Gone. So picture an astronomer in that far future. Brilliant, curious, doing everything right. They look up and they see a single island of stars in an empty cosmos. No other galaxies. No expansion to measure, because there's nothing left to watch recede. No afterglow. No fingerprint of a beginning. Every clue we used to discover the Big Bang erased. And so, reasoning perfectly from the evidence in front of them, they will conclude something false. They will decide the universe is a single, static, eternal island of stars. No beginning, no expansion, no Big Bang. A wrong answer, reached honestly, because the truth has been carried out of reach. There's a haunting detail in the math. The most natural framework for that future astronomer to write down, describing an unchanging cosmos, is the very same static model that our own scientists first reached for a century ago, before we knew the universe was expanding. Cosmology would end exactly where it began, with a beautiful, wrong picture of a static universe, which leaves the uncomfortable question hanging over all of this. We think we live in a golden age, the moment when the universe is still readable, when all the clues are still on the table. But how do we know we're not already too late for some of them? How do we know there isn't a clue that dissolved billions of years before we ever looked up, a chapter already gone? Maybe the universe doesn't just permit minds like ours. Maybe it briefly, quietly, left the answers lying where we could find them, and we happened to arrive while they were still there to be read. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.